will be Fred Goodwin. Fred is a fellow scientist in R&D at BASF Construction Systems in Cleveland, Ohio. Fred has over 30 years, only 30? Okay. I didn't think you were that young, Fred. Of experience in the chemical industry, including concrete repair materials. Fred is the outgoing chair of 364 and the incoming chair of 515, and he's also very active on the Repair Committee 546, E706, and 351. And Fred's going to talk about repair, the ultimate sustainability today. Fred?
Thank you, Paul, and thank you everyone for coming. We titled this Repair the Ultimate in Sustainability. I subtitled it Do Unto Your Future Before Your Future Does Unto You. It's a controversial topic. I'll attempt to address a lot of subjects. I don't claim to be the world's expert on repair and sustainability. I put together a lot of research, and by assembling that jigsaw puzzle, sometimes the parts don't fit together too well, but what I've tried to do is create a toolkit of different issues and resources regarding sustainability and repair. I looked at LEED, green building, embodied energy, construction debris contribution to the waste stream, energy efficiency of old structures, historic preservation, what the actual value of a structure is, room to improve repairs, and the fact we are trying to do some things differently based upon sustainability. But like the sign says, there's a right way, there's a wrong way, and then you can just run in circles too. Sustainability has several definitions. One that I liked is it's an integration of economic, environmental, and social systems into a perpetually healthy, maintainable system. The classic definition is the ability to meet the needs of today's people and environment without compromising that of subsequent generations. That's not the same as green building. Green building is increasing the efficiency of building resource use, that is, using less energy to do the same thing, less water, reducing the impacts on the health and environment through the life cycle by improving siting, design, construction, operations, maintenance, and removal. In other words, green building is only one part of sustainability. The big dog, the 600-pound gorilla in the United States, is US GBC. They have the LEED certification system. It covers a number of different types of certification. The one most relevant, surprisingly, is new construction for the repair industry. One might think existing buildings, operations, and maintenance. That's not really true. That deals more with how the building operates as it goes along, less to do with changing things in the building, which is what we do with repair. Again, they deal with sustainable sites, water efficiency, energy, innovations, and design. Bear in mind, LEED from USGBC is a green building certification system. It's using strategies that are designed and built to improve the performance. And concrete is a pretty darn green material when all comes down to it. Portland Cement Association put together this nice little summary. We create sustainable sites with concrete. We have good thermal mass and infrared reflectivity characteristics. We can use a lot of recycled materials. We produce it locally, and we are extremely good at durability in that it doesn't rust, rot, burn, survive floods, and vermin don't get at it very easily. These are good things, but if you look at the LEED certification system for new construction, and this is my opinion, not that of my employer or anyone else, if you use a LEED accredited professional, you get 1 point, but the use of a LEED system, LEED certification, tends to increase the construction cost 5 to 7%. On the good side, that has a net present value of greater than 50% after 20 years. It takes a while to get your payback, that's what it's saying. I get a point for reusing and maintaining 75% of existing walls, floors, and roofs. I get the same number of points by putting in a bike rack. I can get another point by reusing and maintaining 95%. Durability, I can get 1 point for durability. That's the same as putting in showers in a changing facility. Let's see, energy performance. They do give points easier for renovation than for new construction. This is good, and you can get up to 10 points. By carefully managing construction waste management, diverting 50% of it for reuse, you can get the same number of points as you do for using renewable resource wood. And if you apply for credits demonstrating technical performance, you can get 2 points. But bear in mind, you're dealing with another bureaucracy that's always changing its rules. It's not to bash LEED. It's a good system. It's just not especially favorable for the repair industry. Buildings do consume a huge amount of our energy, even more of our electricity. LEED is really for buildings and neighborhoods. A lot of our concrete goes into infrastructure, which it really doesn't address directly. Looking at buildings, the percentage of floor space of the U.S. building inventory, that's how many structures are built, how many buildings, versus the year of construction. We built a lot of stuff that's still around in the 80s, a lot of stuff still around in the 70s and in the 60s. In other words, there's a lot of older structures. How do they consume energy? This gets really interesting. I know this is a busy little table, but heating, cooling, ventilation, and so forth. Well, back in 1920, they didn't use a lot of air conditioning, so they're very efficient when it comes to cooling. You opened a window. Heating, a lot of them used oil heat, less efficient. And this excludes malls. But if you look at the energy consumption, this is graphing out the totals from the chart in trillions of BTUs versus the age of construction. The energy hogs were built in the 90s, the 80s, and the 70s. In other words, older structures don't always consume a lot more energy. Another way of looking at it is delivered energy. This comes from a different source, so the numbers don't exactly align. And throughout the presentation, I've included a lot of links. If you want to go check the facts, if you want to go do your own research, this is an encouragement to do so. The million BTUs per square foot versus the year constructed. Again, it comes back to the energy pigs are right in here. That's showing it graphically. Until we get to the year 2000, buildings built prior to 1960 tend to be more energy efficient. Historic preservation. There's a lot of very interesting facts about this. I highly recommend reading a book, The Economics of Historic Restoration by Daniel Revetka. You can get tax credits for doing historical restoration. You can increase the property values. It's more labor intensive. It's more specialized to do historic restoration than new construction. Higher skills are required. Guess what? The folks that are doing that are spending the money in the community where they're doing it. They're local labor. So you get a big bang for helping the local economy. You also can create the opportunity for heritage tourism. When you go somewhere on vacation, do you go look at the latest and greatest, newest shopping mall? Maybe you do, but you also tend to look at the things that were built 200 or 300 years ago. That's what's interesting. There's a high rate of return for doing historic rehabilitation. Furthermore, rehabilitation in many sense is less dollars per square foot than new construction costs. Tends to use less energy than new construction, according to the University of Michigan. Your infrastructure is already in place, so you're not having to replace sewers and electric lines, water supplies, roads. Preservation's popular with the public. It's easy to get tax dollars voted for it. Older buildings are more energy efficient. They're built with heavier materials, and they've survived the test of time. They've been there a while. It means that design worked. And a lot of other facts. It instills pride. It saves on maintenance costs, especially longer term. Switching topics, embodied energy. Anybody know what embodied energy is? Okay, Mr. Armbruster?
It's the energy that went into and is in effect there in that building.
Yes. Fancy definition, to say what you said very elegantly, sir, is it's the energy used throughout the life cycle of a material. That's mining the ore, refining it, processing it, fabricating building components, getting them to the job site, installing them, commissioning them, utilizing them, maintaining them, removing them, and disposing or recycling of them when everything's done. That's right from ASTM. Different kinds of buildings have different amounts of embodied energy. This site, thegreenestbuilding.org, has a lot of very interesting facts about embodied energy. But laboratories, libraries, hospitals, the more durable structures have a higher amount of embodied energy. That's not too surprising. Where residential construction has a lot lower. You build it out of wood. Going through this example with a 100,000 square foot high-rise apartment. I chose this example because it's probably built out of concrete. You're building something like that. Well, the calculations on the model show 74 million MBTUs. I'm just going to call it 74 million MBTUs for the sake of not having to deal with exponents or millions of millions and so forth. Now the model calls out demolition energy separately. To tear down a concrete structure takes 12,000 MBTUs of that size. And let's say we build it back about the same way. 74 million MBTUs to build it back. You can argue that new construction methods may use less energy or more energy, but let's just assume it's in the same ballpark. That's 148 million MBTUs to tear it down and replace it, and the embodied energy in the structure. Going back to the previous chart, buildings constructed from 2000-2003 was the most recent that I had figures for. They used 61.7 MBTUs per square foot per year. So that translates to 8 million MBTUs per year. I calculate then it takes about 23 years to get back the embodied energy in that structure of operation cost. Bear in mind, LEED certified buildings have 25 to 30% energy usage, not used in these calculations. I didn't make that assumption. The most sustainable building may be the one that's already built. As I said, utilities and services are already there. Energy has already been used to fabricate the components. That is, I burned a lot of gas to fire that brick. If I throw that brick in the dumpster, there's no way I can ever get the energy back to make it again. If I can reuse it, I don't have to burn more oil or gas to make more bricks. I don't have to take the energy and dispose of it. And I don't have to fabricate new components. We talk in energy savings a whole lot about windows. Now, this is the American Concrete Institute, ACI International, so we don't talk about windows. But if I look at new windows, they're double glazed, filled with argon gas, having an aluminum frame and a polyurethane gasket inside. An old window has a wooden frame and is a panel about 8 by 10 inches. The new window is a panel 4 foot by 6 foot. Somebody throws a baseball through it. I can replace that one little bitty panel a whole lot easier than I can that great big panel. Demolition. Like I said, the model calls out demolition separately. Let's just look at how much energy it takes to tear down a concrete structure. To tear down a wood structure, the site tells me it takes 1/5 the energy. Takes 1/16 the energy compared to a concrete structure to tear down a steel frame structure. Unfortunately, the model doesn't go into a whole lot of detail as to how they got those figures that I could find. Solid waste. One of the interesting facts about solid waste, municipal solid waste, MSW, that's the stuff that's in your trash can every morning at the end, Monday morning for the dumpster to come and pick it up. All kinds of figures about that, all kinds of compositions and what we throw away and how that volume is changing. This stuff, non-municipal solid waste, I found it really, really hard to find information on it. It consists of construction and demolition debris, foundry waste, coal ash, think fly ash, flue gas desulfurization waste, and other kinds. Easy to find the figure. We produced 251 million tons of municipal solid waste in 2006. However, the hard figure is industry generated and disposes of about 7.6 billion tons of industrial solid waste per year. According to the EPA, non-municipal solid waste is more than 30 times that of municipal solid waste. The environmental impact of repair and renovation, statistics show 170 million tons of solid waste is from construction activity. 42% of it comes from renovation. 20% of the total of construction and demolition debris is from our industry, folks. Of this demolition waste, construction demolition waste, 44% is from renovation, whether it's residential or non-residential. What's the forecast? Here's the population growth in the U.S. from 97 through about 2010. There's the waste generation. We're getting a little more of it all the time. We're doing better at recycling, but total waste is growing. That's total solid waste. Furthermore, the amount of built space in the U.S. is going to grow from the 300 billion square feet of space, structures, buildings that we had in 2000 to about 430 billion square feet by 2030. Of that growth, that amounts to 130 billion square feet of new construction and replacing 25% of our existing building inventory during that time period. We're going to tear down a heck of a lot of the stuff that's standing. But the economy has a big factor in this too. Remember, we're in a recession, depression, something like that. Well, if I owned a building today, what was it worth in 2008? The light blue line is residential. The green line is commercial. Average selling price of commercial construction peaked in about December of '07. at about 185 on this index, and now we're down to around 100, 110, 120. Okay, I got a building worth $10 million in 2007. Today it's worth $6 million. What do? I maintain, repair, restore it. We're in a growth industry. Running some figures on that. Two-story office building, 83,000 square feet. Granted, it's clay brick. That's where I found the example. $16 million replacement cost. And if you calculate that out, it's right about in the middle of what commercial building estimates to be costing. I'm not an engineer. I don't build things. Tell me if the figure's right, wrong, or in the ballpark. But about $200 a square foot. Same building, a 50-year maintenance or repair cost summary shows replacing it $16 million, keeping it maintained is $11 million. The biggest return on investment for concrete repair? De Sitter is an interesting guy. I think he's a professor over in Denmark. Came up with this law of fives, which is just really, really elegant. He says if I invest $1 monitoring a structure, that corresponds to $5 invested on preventative maintenance before corrosion starts, or $25 spent on repair after localized corrosion initiation, or $125 spent after I see spalling and leaking rust out of cracks. Many of you are more familiar with Tudi, Swedish professor. He says if I fix things during the corrosion initiation phase, it's got a lower cost and a longer lifespan than waiting a while. And doing nothing at all is the highest cost with the shortest lifespan. Good news of that, here in the concrete repair industry, that gives us a whole heck of a lot of job security. Tudi also says if I look at service failure, when do I do my reactive maintenance? If I do it infrequently and very disruptive, as I take a long time to do major repairs, I have a very long period of service interruption and a higher cost than doing a little bit along proactively, and the total amount of time for service interruption is really shorter. I can sneak in, do a few things on the weekend instead of waiting until it's really bad and having to shut it down for 3 or 4 months. How much is it going to cost to fix our infrastructure? Many of you are civil engineers. You're probably familiar with the report card that says $2.2 trillion to bring our infrastructure back to as good a shape as it was in 1980. Well, that's $7,000 a person if I divide that out by the current population of the U.S. That's not making it like new. That's just as good as it was in 1980. Oh, so the stimulus is going to bail us out. We've pumped a lot of money into that, right? Well, there's my $2.2 trillion. We plan to already spend $903 billion on our infrastructure. The stimulus is projected to pump $71 billion into that. It still makes a shortfall of $1.1 trillion. It's a drop in the bucket for what we need to do. What do we need to do? 26% of our bridges are structurally deficient or functionally obsolete. Go talk to somebody in Minneapolis about that. Poor road conditions cost us $67 billion a year in repairs. We spend 4.2 billion hours a year stuck in traffic. That costs us $78 billion a year to the economy and lost productivity. Hope you don't live downriver from a dam. There's 4,000 of them that are deficient, and more than 1,800 of them are high hazard, and they're going bad faster than we're fixing them. Locks and waterways. 50% are currently functionally obsolete, projected to grow to 80% being obsolete by 2020. Yet the savings of transporting materials by barge saves us an average of $10 a ton versus other shipping methods. We're not necessarily maintaining and fixing the things that are saving us money. Now, back in the 70s or 80s, there was this wonderful movie called Network. It's about a network broadcaster that goes totally insane on the air and he starts shouting, "I'm mad as hell and I'm not going to take it anymore." It's kind of how I felt about it when I saw these statistics. Vision 2020 says the annual cost to owners for repair, protection, and strengthening is between $18 and $21 billion a year in the U.S. Why does concrete fail? The 3 Ds: design and construction errors, deterioration, and damage. They all work together. Study by ACI, granted it's from 1979, most recent information I could find. The big 3: insufficient knowledge, carelessness, and underestimations. It's one way of looking like why we're here, to try to learn, to try to fix this issue. Another way of answering the question, why does concrete fail? Concrete itself fails because of mechanical issues, chemical issues, physical issues, and fire. The other biggie is reinforcement corrosion, carbonation, chlorides, and other bad things getting into it, stray currents. How many repairs fail? This is a quote from the U.S. Army Corps of Engineers, Reamer CS2. A little more than 50% of the repairs performed on the core structures are performing satisfactorily. They don't feel it's that unusual. More recent study from the BRE, this ConRepNet was an industry consortium in Europe. They got as many problems as we got. They looked at 215 case histories. They found 50% of the repairs were successful. Those that were successful tended to go downhill in a hurry. How did they fail? Biggest problem was cracking. Corrosion, debonding, alkali aggregate reaction were other factors. That's kind of the chicken and the egg. Does corrosion cause cracking or cracking cause corrosion? Don't debonding and cracking kind of go together? The first thing I see with AAR is usually the cracks. Came up with 17% are either the cause or the effect of cracking. So where do we go from here? Gaze into the crystal ball. Improved technology. Back in the stone, way back when, we built things out of wood, mud. We know a lot about doing that. We know a lot about building out of stone. A lot about building out of masonry. A whole lot about building out of steel. Yet today we're in the concrete age. Our tallest buildings are based out of concrete. Our longest bridges are concrete. Our largest dams are concrete. Yet the amount of knowledge we have about it as a construction material is still growing. We're still learning new things every day. A lot of room for improvement compared to our competition in building materials. Sustainability. Reduce waste, improve efficiency, that's green building. Reuse. Adaptive reuse of structures, deconstruction of existing structures, salvaging building components. Renovate, rehabilitate, restore, and repair, the 4 R's. Recycle. We're learning a lot about cement extenders, about concrete, about adaptive reuse. Concrete repair is a growing business, and we live in very exciting times. Construction industry itself is changing. Back in the good old days, it was design bid. Engineered set, draw up a bunch of plans, call up contractors, how much it's going to cost to build it this way. We're now in design build. Work together, come up with a solution. A lot of newer things, they're putting in a maintenance plan. Biggest bang for the buck if you have a new structure is put in a maintenance plan and follow it. Do that proactive maintenance. We start building new reactors, nuclear reactors, we better be thinking about how to take them apart when we're done with them too. It's one of the problems our forefathers passed along to us. Where we would really like to get to, design, build, maintain, and rehabilitate. Plan for what you're going to do with the structure when you're done with it. So I've kind of included a library of a few things for some further reading if you're interested. Okay, I really like Dilbert. I have a Dilbert calendar. It's one of my favorite cartoons. They say that people fear public speaking more than they fear death. So technically, if you kill the guy that's giving the talk, you may be doing him a favor. So after that, I'm going to say, does anybody have any questions? Thank you very much. Are there any questions? It's really frightening. You get up here and you talk and everybody nods their heads and then nobody has any questions. Okay, thanks.